Very good afternoon, all, and welcome to the class. I'm sure all of you have done now the quick sort implementation and you have understood the basic working and for equality issues also. Those who have completed the implementation, good. Those who have been able to run that and test that well, very good. For those who have not completed or who found some difficulty, I'm going to show you the demo into the DivCPP and then we will resume further with the next topic. So let me just minimize this and come to here is the DevCPP screen, which I would like to demonstrate to you. So basic program, we have already seen the partial code also I have given, and now you can easily see this is a condition which will be normal. This also I have already shown into the partial code, and we can think of now the condition to be this. Ideally, I will say here, normally you will have a habit of writing the condition this way. Array p less than this and this. I'll say this is a slightly incorrect, and we should prefer, or we should always have a practice that we write the condition this first and then have the array I less than pivot. You might say it is one and the same thing, both conditions are in and, but yes, that will make a difference. First, the i's boundary should be checked. If array is within the boundary only, then this condition should be checked. In worst scenario, there can be a situation when you jump out of I and then later array I is checked, and if you are going out of array boundaries, and memories could be such that you could lead to a wrong place which was not a part of array itself. Say if your array was just tight and up to the last element it was filled, and if you go beyond I, then you will be stepping out of the array limits, and that will be in illegal memory access. But if you are writing I less than equal to end first, it ensures that I never goes beyond the limit. And if I is going beyond the limit, the second part of this AND condition will not be executed at all, will not be checked at all. If this condition becomes false, you will come out of the loop. So it will safeguard you from going to illegal memory access. The earlier, when you have written array I less than pivot and I less than equal to end, you first went to check the illegal memory address of array, and later you found that I was out of limit. And that could lead to some kind of a memory trap or segmentation fault in some special situations. If you don't understand it, not to bother much. Later you will slowly realize these facts. But yeah, this is what I did. Then similarly do j minus minus, and if I is less than j, then I have this, while this swapping of array start with array j and then other two elements being called. So that becomes a fairly simple code, and I'm sure you are able to do this without much difficulty. So now let's resume to our further discussions, what we are going to talk today, and next, what is our topic. So having done the sorting part, we normally say in data structures, we normally have a topic which is called as searching and sorting. This is a common chapter, or as a part of syllabi everywhere, you will have searching and sorting being as a one complete unit of syllabus. Sorting we have discussed, and heap sort is another sorting algorithm which we will talk later, because this will require some concept of a trees to be used. So that we will talk later. Other useful sorting algorithms we have discussed. And now we talk of the other aspect, searching. Normally, searching could be covered earlier also, but searching will also use some kind of a recursion also for certain special logics, and that also could be useful. So we will discuss now and understand all those concepts in a single go after now. So primarily searching is of two types. One we call as a linear search and another we call as a binary search. Linear search, knowingly or unknowingly, you have done already. Linear search simply means you have a list and you want to find whether a particular element is present in the list or not. Say you have data 20, 15, 30, 50, some random list, not sorted list, not in any particular order. It could be any data anywhere. So if I have data like this, then maybe I'm interested to search, let's say for 40. So search 40, effectively what you do is always start, let's say I from here, compare with the first value. If you found, you will say, okay, found it. If not found, then you will proceed I next, I next, I next, I next. Here you will find and you will say, okay, found at index 0, 1, 2, 3, 4. So you will say found at index 4. If not found, say you are searching for some value, let's say 18. So you will say not found here, not found here, not found here, not. You reach up to the last. After this, there is no data left. So you will say 18 is not found. And 40 will be at index 4. This is what linear search means. You have done already time and again, probably this kind of a logic. If it is to be implemented using a function, of course, we will write a function like int linear search. Whatever data you want to supply, whatever parameters, I think now you should be able to decide. And let's say I want to search for variable or value val into this. Say val could be 40 or 18, etc. So my function is supposed to be ideally returning the index if found, and if not found, normally we always say -1, etc. to be returned. How to do that? It's a simple logic. I'm sure you have done time and again. So you will say for I equal to 0, I less than n, I plus plus. And you will simply compare if ARRI equal to the val being searched. So of course, now val should be a parameter, n should be a parameter, array should be a parameter. All that becomes implied in terms of modular programming. If the value is found, you have to tell at which index it was found. And index is to be returned back. So I will say simply, I will say return I. That tells that it was found at this index. On the other hand, it is possible that you could not find this element anywhere. Full loop was exhausted. So if you reach to this place, it guaranteedly means element was not found. In that case, you will return -1. So effectively, -1 is equivalent to saying not found. And in main, you should be able to use this concept and tell that element found and at this index. Otherwise, return status is -1, meaning not found. For example, if you are searching for 18, so you will say I equal to 0, array 0 equal to 18, no, then I will be incremented. Array 1 equal to 18, no. Array 2 equal to 18, array 3 equal to 18, no. 4, 5, 6. Array 6 not equal to 18. Again, you went back. If was false, false again went. And now I becomes 7. This was last element. Array becomes 7. 7 is not less than 6. So you will come out of the loop. And once you are out of the loop, you straight away come here and say not found. Any value found was 40, 35, 20, wherever found, loop will stop, program or this function will terminate at this point and value will be returned. Linear search you have done time and again. Binary search is what we will discuss today in more detail now. So binary search. First thing is what it requires is what is a prerequisite or what is a requirement over the data. It has a special requirement. The list must be, list or array, whichever you are using, must be in the sorted order. So we have already studied sorting. Now we can understand that we will do the sorting through any logic. And this binary search requires that if the list is already sorted, only then binary search will work. The reason of binary search is simple. It will be faster than linear search. In linear search, especially if the element was not found, you cannot conclude it early and you have to go through the whole list. Once you go through the whole list, only then you can say not found. Binary search will be able to conclude that much faster, but of course, that requires a list to be sorted. How it will be able to conclude? Let's understand. Say we have some data. Let's say I have a list 5, 10, 15, 20, 25, 30, 35, and let's say 40. So this is index 0, 1, 2, 3, 4, 5, 6, 7. Let's say I have total n equal to 8 and elements are 0 to 7. But you can say they are sorted. For the time being, I am assuming unique values, but yes, there can be non-unique also, duplicacy also. But searching will mean I just want to find whether element is present or not. So multiple presence doesn't make any difference to me. So I'm saying now search for, let's say, I'm interested to search for 35. Let's assume 35. How do we do? So we will say it will use the concept of a binary partitioning. Effectively, sorted data will say, first of all, I will compare the value with the middle element. I will calculate middle. Middle will mean 0 plus 7 by 2. That is a 3 because it's an integer value. 3.5 will mean this to be 3. So 3 means your middle is at index 3. So I will say compare it with the middle value, 20 versus 35. So I'm going to check that. If the value found, straight away answer ready. If in this case, like it is not ready, so the good part about this is I can guaranteedly claim because 35 is greater than 20, it is guaranteed that 35 will not be present into this side at all. Into the left sublist or left of mid, it will not be present at all. And into the right of sublist, into the right of mid, or in the right sublist, it may be present. So my focus will be eliminate or forget about this left half, focus on only one half. So every time I will be able to focus on remaining. How to focus on this? Again, same process. Again, go to the middle of this list. Middle of this list will mean this is a 4 plus 7. So 4 plus 7 by 2 will mean 5. So mid will become as a 5. That will mean compare with 30. So I will say is val equal to a double r mid. So val is now 35. Mid is 5. So a double r 5 becomes 30. Again, not equal. Not equal means still I have to repeat value 35. It can be, if at all present, on the right of 35 because 35 is greater. So that case I will make the logic, and then I will say, so I will say if equal, effectively found, else whether if my val is less than array mid. So I have to search in one direction, search in left sublist. Or otherwise, because val is greater, guaranteedly, else means guaranteedly greater. So I must search into right sublist. This is more or less the working of this. And how to search in the left or right side? That can be the similar process, but it can be iterative as well as recursive. So 30, again search in the right sublist, 35 and 40. This is index 6, 6 and 7. I will again find mid. Mid will be 6 plus 7 by 2. That means again 6. And then I will be comparing 35 with the corresponding array mid. Mid is now, so I'll be having if again, val equal to array mid. And mid is now 6. So array 6 is 35. Val being searched is also 35. They match. I will say element found. Found means I should return index 6. Index must be returned back. So that is what I want to try. So this is what is the binary search. But remember, the data is sorted. And of course, we are not counting the time which will be spent on sorting the data. It is assumed that through some previous operations, etc., the data is already in the sorted order. So my searching will become faster if the data is already sorted order. And that's what we are assuming. So if I have to do programming, of course, I will make a function. So just like a linear search, it will be called as a binary search now. What parameters I need, of course, I can accordingly decide. But accordingly, I can plan and make those parameters. What I need, I said, first of all, whether I have to repeat the process or not, accordingly, I have to make the logic. So this can be now recursive, as we have said, repeat the same process, or it can be iterative also. Iterative means using loops, and that is also equally easy. Because what I say, that repeat the process doesn't mean recursively repeat. I could say again find middle of the right sublist, again compare and reduce your list. So effectively my list boundaries will be redefined. For the left sublist, the boundaries will be changed accordingly if needed for the right sublist. Let's see whatever logic is clear to me, we will start making and then we will complete the logic. So let's start making iterative logic first. What I say, I have definitely said that I needed mid equal to start plus end by 2. So I need start as well as end. I can make 0 to n by 2 as a starting value. And what I wanted to say was that if val equal to array mid, I'm clear this is definitely going to be somewhere. What to do? Element is found. Means return. Return what? Wherever the element is found. That index is mid. So the index on which element present is returned. Function over, need not repeat. Else what to do? Else I have to search either in the left sublist or in the right sublist, in the first sublist or the second sublist. How? Based on decision. What decision? If val is less than array mid or not. If val is less than array mid, means value, if at all present, will be in the left sublist. Left sublist means what? Let's say this was my 20, this was my middle. Middle is at index 3. Left sublist means what? Left sublist means earlier the list was 0 to 7, but now the list will be 0 to 2. And if I want these indexes to be readjusted, so I can easily see once I have done this, what is my new list boundary? 0 to mid minus 1. 0 was, or 0, I'll say in general, it was a start to end earlier. Now one list is start to mid minus 1 and other list is mid plus 1 to end. So one of the list is to be seen for the future repetition process. If the value is less, I need to search into the left sublist. That means my left sublist will end at point mid minus 1. So I can redefine my boundary to be mid minus 1. Else what? Else I have to search into the right sublist because val is guaranteedly greater than array mid. So it has to be present at all if present into the right sublist. Right sublist starts with mid plus 1 and continue up to end. So end boundary is okay. Start boundary has changed. So I will say start of the new list is now mid plus 1 instead of a mid. And now what I have to do? I have to effectively repeat. So repeat means iteration. Repeat means loop. And how long should I repeat? So I can think of having this to be a kind of a while loop. And what should be the condition? As long as a list has any single element left, I need to search. Probably I could find. So if the list has any single element, I should search. Once the list has no element, I will come out of the loop. So if I reach to this point, it means list ultimately became empty for my searching of that value, and I can guaranteedly conclude now the element is not present. Not present means I will return -1. Why do I say this? The reason is simple. Let's say I was searching for some value 33 instead of 35. Let's take 33. Say val to be searched is 33. What will happen? This is 0. This is 7. Middle becomes this. And you find 33 equal to 20. No. Then you say else 33 less than 20. No. That means else 33 is greater than 20. What did you say? Else you said end equal to mid -1. End equal to 2. This means now my end comes to this place. Start is this place. Earlier end was here. Now end has shifted to this point. Because, if I said else was start equal to mid +1. That means start changes to 3 + 1, that is 4. Because I'm searching for a bigger value than 20. So I will be going into the right sublist. So earlier start was here. End will continue to remain here. Start will shift here. So I'm going to search 33 into this list. Definitely no need to search this side. This way I have removed half elements almost every time. So that will be obviously much faster than linear search. Every time I will be able to reduce the list to half size. Now start equal to 4. So this is my index 4. Again, loop, list has more than one element. So I will repeat, again check. If val equal to array mid, now mid is to be calculated. So mid will become 4 + 7 by 2. That will become 5. Array 5 is this element. So I will say 33 versus 30 not equal means else again 33, if at all possible, has to be into the other side. So I will say my again start changes. It becomes a mid +1. Currently mid is 5. So start becomes 5 + 1, 6. So now my focus of the searching comes to list 6 onwards up to 7. Only this list to be focused. On the left of 30, it was impossible. Again, now mid to be calculated. 6 + 7 by 2. That becomes again 6. So I will say, now I will compare val equal to array mid. Array mid is 6. That is 35. And I am searching for 33. 33 equal to 35, no, else. 33 is less than 35. That means the end boundary will be changed, because if at all 33 present, it can be on the left of 35. Left of 35 means now my end boundary is changed. End equal to becomes mid -1. That is 6 - 1, 5. Remember what was the start at this point? Start was 6. So for this particular repetition process, my start was 6, end was 7, and now end has changed. So my list is effectively now having start as 6 and end as 5. That means effectively list empty. Not even a single element present. Incorrect data for list start and list. So accordingly, my while condition has to be written. But I can conclude that 33 was supposed to be on the right of 30 somewhere. Hence, we targeted to go on the right of 30. 33 is supposed to be on the left of 35 somewhere, but on the right of 30. That was already concluded. And in between 30 and 35, there is nothing. Hence, list is empty. I must return -1. So this is how my unsuccessful case will come, and this is how I will come out of the while loop. If at all element present, at some stage, we will reach to that element as a middle element, and at that stage, this return will execute. For my successful cases, it will work correctly. For unsuccessful cases, ultimately I'll come out of while loop, and that will be the place where I will say return -1. Having said that, let's understand the iterative, the recursive version also. So recursive also it is possible. How? Of course, recursive will mean we have to take care of the conditional call. Recursion should never be called unconditionally. So conditional will mean what? First of all, of course, if I assume list has at least one element, only then I am going to continue. If the list has a 0 element, of course, nothing to be done. So I will have if condition. If list has at least element. So condition is more or less same the way we have seen earlier. So I will say again, my function is int binary search. Parameters can be again similarly defined. More or less, it must be almost same as we have already been discussing. So I'll say if list has some element, then what to do? Calculate the middle. So my middle will be calculated, start plus end by 2. Same as we have been doing this. The only thing is here it is if, no while, because I said it will be recursive. Hence I will say I will check if work to be done, either the element is in the left middle side or recursively to be solved. Is it in the middle or not? I will check if val equal to a double r mid, and because list has minimum one element, mid will be guaranteedly pointing to that one element. If it was single, more than single, it will point to the middle element, almost middle. If found, of course, we have to say return mid. Else what? Now, else there are two cases. One case, if val is less than array mid. Now I say if val is less than array mid, I don't say repeat the process. I say recursively find val into the left sublist. So I will say recursively find val in left sublist. I'm intentionally not writing the code or the syntax because I have one important point to make. And else I will say, accordingly, recursively find the val in right sublist. In the right sublist. Why I'm not writing the syntax now, I will explain. So that's it. This is the overall process. If successful, you have the return value. Now, if unsuccessful, when should I say return -1? But now I can't say that I should write return 1 -1 here. Then return -1 will be only possible when I am able to conclude. If this recursion works, this might find a value in between. This also might find a value in between. So it is possible that somewhere in between this, it was able to find a value. It was also possible it was not able to find. So it is possible that from here either correct index is returned or it will return -1, probably some cases. Index or -1, you never know. It will depend. So that means in this case, returned value must get used. So if you are doing such kind of thing, one important point to remember always is if a recursive function is returning something, if a recursive function has a return type, you have to make sure that you don't commit a mistake by ignoring that. Each recursive call must return a return value, and each recursive call returned value should be used by also. What does that mean? I will now explain. This statement you could think of writing binary search recursive call with certain parameters. Almost okay, but this is supposed to return something. Are you using that returned value for some decision? You have not thought. So this call simply writing with binary search will be incomplete. Similarly, this call writing will be incomplete. So this will be returning some status, which could be -1 or index, and that also must be returned and used. Here also the same process. And you can't say that I can simply come to this place. Yes, if you come to this place, it means list was empty. So at this point, you have a guaranteed answer that it was, let's say, not present. But that indirectly has to be contributed and used for each of this call also. So here you can't simply call binary search. This must be something equal to binary search. And that's equal to wherever you are returning, say status or some variable you use. This status variable must be used for your decision. In this case also status should be returned. In this case also status should be returned into variable start status or anything. And then you should use that also. Having said that, I think I will stop here. So give you homework. Your homework has to be implement binary search in both ways. Of course, assuming your input supplied will be sorted data. So give input as a sorted data only. Implement using iterative manner or iterative logic. And then also implement recursively. And ensure that both work well for successful as well as unsuccessful data, for successful as well as unsuccessful searches. If you are searching for a data which is present into the list, that we will call as an successful case. And if data is not present into the list, that will be called as unsuccessful search. So you must ensure both correctness for successful searches as well as unsuccessful searches. With this, I will stop and I will say all of you must try, because we have some time left today because today's lecture is smaller. So I am going to demonstrate the correct code for iterative as well as a recursive binary search. But before I show the code, I will say code yourself, pause here the video and try first yourself. Once you have completed your implementation, you will be almost good in completing iterative at least. Try to complete the recursive also. If you are not able to complete, think again and again and try, hit and trial and do that. And you will be able to make 90% of the code correct. Once you have completed, then you can see the demo now being shown. So once you have completed, and if you want to see the answer, sample answer, now you can see after this. But before that, I'm expecting all of you to must have tried of your own, completed iterative at least with full correctness. completed recursive with almost full correctness or at least partial correctness. And rest for what I told will be now I will discuss through the dev CPP. So here is iterative version. I already said that enter the values, number of elements. So the values have to be in the sorted order. You have to ensure that while giving the data, you must put that in the sorted order. And based on that, of course, I will say, no, I will not use this syntax. I will change this to have the correct syntax the way we have been using. And this way, I will be writing the reading part. Once I have read, I will say the value to be searched. This is a val to be searched. And then I'll say call that. Index being returned. If index is -1, I'll say element not found. Otherwise, element is at this index. Calling this with the start as 0 and -1, and that way I can have. So even if I don't have these variables, still it is perfectly fine. There is no necessity to have these variables declared because I'm directly passing this. More important part, binary search function. So parameters, now I should be able to decide condition. As long as list has a single element, I need to repeat. Find middle. If middle found, return. If val is, I'll prefer to write it like this. If val is less than list mid, then I will say the left sublist to be used, else right sublist to be used. And if I reach out of while loop, it is return -1. So this becomes a simple logic. I can see that it is compiling well. It can run. I am not showing the execution. Recursive. All remaining initial part is similar. I'll say this is what I'm more interested at. So my initial part all remains same. My binary search logic also same. Condition also same. I'll say if start less than equal to end, mid will be computed. If list is equal to this, I have found the element. Otherwise, I'll say if val is less than list mid, I have found the element. I can find the element into the left sublist. Left sublist means start to mid -1. Now, this is something where I was saying each call must return a value. So I'm having the value returned by this call to be called as a status. In that case, a status will be returned. So I might not reach to this else part. If this binary search was able to search, it will return me 1. And this return value will be, return me the index, and that index will be returned back. Similarly, if I'm searching into the right sublist, that status will come from that recursive call. If that was found, I will say, yeah, element found. If not found, I will say not found. But sometimes I will reach to a situation where list is empty. Then I will compute straight away else, and I can conclude that in that case, return is -1. If I'm not going into else part, this -1 will not be executed, either this return or this return or this return. Of course, slowly, wherever not found will ultimately reach to the empty list. From that empty list, -1 will be returned. That recursive call will receive -1 from those empty lists. And from those recursive calls, either this side or this side, the same -1 will become the status and go back. So this is there. Most of you could have thought of doing like this. Most of you could implement like this. And probably still you could get correct result for most of the inputs. But this code is incomplete. The reason I have already explained. So ideally, I should make sure not to miss such cases. With this, I think I'm completed with this code. So I can stop here now. And from next class, we are going to start with the stack as a new data structure. So more serious programming will start. I'm expecting all of you to complete all programming, arrays and functions, recursion and modular programming and concepts to be clear. And then we will start using these concepts into my further coding, which is stack-based programming from the coming class. Bye-bye. All the best to all of you.